earlier in the course to illustrate the relationship between observables and observers. Observers are really pretty simple objects. I'm showing you here just about everything you need to know about them. They're objects that implement an interface containing three methods: next, error, and complete. That's it. If you've got an object with those methods, you've got an observer. When you want to receive data from an observable, you pass an observer to the subscribe method on that observable. When it has data, error, or completion messages to communicate to the observer, it calls the appropriate method on the observer. Let's now look at the actual syntax required to do this. Here I'm going to create a very basic observable that just produces the values stored in an array. I now need an observer that will process those values. Remember that an observer is just an object with three functions. I'll create a new variable and assign it an object literal. The first function I'll add to this object is named next. I'm assigning it an arrow function that will be passed the value being produced by the observable. My implementation here will just log the value to the console. My observer also needs a function named error to handle any errors produced by the observable. The error will be passed as a parameter to the function. Again, I'm just logging it, but with an error label as a prefix. The last function I need on the observer is named complete. It doesn't accept any parameters and is where I could write any cleanup code I might need. Here I'm just logging that the observable is all done producing values. In order to actually cause the observable to begin executing and producing the values in the array, I need to subscribe to it. I do that by calling its subscribe method and passing it the observer I just created. Each value in the array will be passed to the next method on the observer, and the output will consist of each number in the array being logged. Writing some code that follows this pattern is probably one of the first things you'll do with RxJS. You'll also probably do it with an observable that was either returned from some framework function or that you created from an array or an event. However, you can also create your own custom observables when you need precise control over how data is produced. To do that, you'll work with a second object known as a subscriber that happens to implement the same interface as the observer object. Let me give you a sense of what that code might look like. Once you've imported the observable type, you can create your own custom observable by calling its create method. That method accepts a function that will do the work of sending values, errors, and completion messages to an observer. I've written this code to pass an arrow function to create. The function accepts a single parameter that I've named subscriber. This is the object that implements the same interface as the observer. It has methods named next, error, and complete. Inside this function, I can implement any logic I want and use the subscriber object to send information to observers that subscribe to my observable. If I've got a new value I want to produce, I just call the next function on the subscriber and pass it the new value. If I encounter an error, I can call the error function, and whenever I determine my observable is done producing values, I can call complete. Under the hood, this will call the corresponding methods on the observers that subscribe to my observable. I'll show you a working example of this in a demo in just a few minutes, but let's next take a look at operators and the syntax you'll use to apply them to the output produced by observables. Operators are functions that let you manipulate the values produced by observables. I first mentioned them earlier in the course while going over the benefits of RxJS. Observables seem to get most of the attention, but operators are certainly one of the building blocks of the library, and RxJS would not be nearly as useful or as popular without them. Since I covered the benefits of operators earlier, I want to get straight to the syntax for using them here. Before you can use an operator, you've got to import it. All operators are imported from rxjs/operators. Here I'm importing the filter and map operators. I'm going to use the from function, just like I did in the last clip, to create an observable that will produce the values stored in an array. As I've already shown you, I can then create an observer and pass it to the subscribe method on the observable to begin receiving the values. However, if I want to apply an operator to the data coming out of the observable, I call a different method on it named pipe. Inside the call to pipe, I use the filter operator just like a function. Here I'm only allowing values greater than 0 to pass through the filter. The pipe function will apply all of the operators inside the call and return a new observable that produces the resulting set of values. You can then call subscribe on that new observable and pass it the observer that should process the values. In this case, the observer will only receive the values 1 and 2. If I wanted to apply more than one operator to the original observable, I can just add a comma after the first one and add another. Here I'm taking the values that remain after applying the filter operator, and I'm applying the map operator to them and multiplying each of them by 3. After subscribing to the resulting observable, the values logged to the console will be 3 and 6. There are over 100 operators that ship with RxJS, and you can also create your own if you determine you need some custom behavior. I'll show you another example in a demo in just a minute, but I first want to introduce you to the final building blocks of the library, subjects and schedulers. Subjects are similar to observables, but have a few important additional features. They're a slightly more advanced topic, so I'm not going to go into great detail, but I want you to get through this course with a good sense of all that's possible with RxJS. At the beginning of the course, I explained the observer pattern and showed you this slide. The pattern describes an object, known as a subject, that maintains a list of the observers that care about the values it will produce. As the subject produces new values, they are each sent to all of the registered observers. At the most basic level, this is what subjects in RxJS do as well, and why they're called subjects. They're also capable of other tricks, but they're really all variations on this ability to push data to multiple observers. Observables can only produce values for a single observer, so we refer to them as unicast. Since subjects can produce the same value for multiple observers, they're known as multicast. There are lots of scenarios where multicasting is useful, and RxJS also includes a number of operators that make it easy to multicast data without having to set up and manage every detail about a subject. Okay, next up I want to introduce you to schedulers. Schedulers are the final building block of RxJS I want to tell you about. Let me start by showing you a line from the official RxJS documentation. A scheduler controls when a subscription starts and when notifications are delivered. Observables can be configured with schedulers to control the execution context for the observable. There are several schedulers available that correspond to JavaScript execution context you may already be familiar with. The queue scheduler causes an observable to execute synchronously. There may be times you want that, but you have to remember that synchronous tasks block the JavaScript event loop and may cause your app to appear unresponsive. The async scheduler will execute an observable asynchronously using the JavaScript setInterval function. This is usually a good choice if synchronous execution isn't required. There's a second asynchronous scheduler option known as the ASAP scheduler. It will execute your observable on the microtask queue. Schedulers are one of those features you really only have to worry about if you're doing something very precise and want to make sure you control exactly how an observable will execute. In most cases, there are very sensible defaults applied to observables, and you can focus more on your data than the context in which it's executed. Okay, it's finally time for some demos. I'll now go write some code and show you some of these building blocks in action. In this demo, I'll show you a couple of options for creating your own observables and observers. Before I start writing some code, I want to show you this very basic project I'll be starting with. Here you can see the contents of my package.json file. I'm going to write my code in a TypeScript file just to make it a little easier to compile and run the code, but I'm not going to be taking advantage of many TypeScript features. I'll run the compiler and bundle the code with Webpack and serve it using the Webpack development web server. The other dev dependencies you see here just enable Webpack and TypeScript to work well together. A little further down, you can see that the only application dependency I've installed is RxJS. I'll start the app using this npm script that just runs the Webpack dev server. It will run the TypeScript compiler, bundle the code, and serve up the application over HTTP. It will also automatically reload everything as I make changes to the code. Inside my index.html file, you can see I have little more than a script tag that will reference the JavaScript bundle output by Webpack. I only have one code file in the project, and it's this index.ts file, which currently has nothing in it. The first thing I'll add to it is an import statement that imports the observable type and the from function that I'll use to create an observable from an array. I'll then declare a new array that just contains a few numbers. As I showed you earlier in the course, I can create an observable from an array by passing the array as a parameter to the from function. The observable it returns will produce each element in the array as a value for its observer. I now need to create an observer. Remember that observers are just objects that have functions named next, error, and complete. I'll create a new variable named observer and just assign it an object literal. Just so you don't have to watch me type so much, I'm going to use a code snippet to paste in the three functions I need. I'm using arrow functions for each of them and keeping them very simple for demonstration purposes. The next function will be passed the next value being produced by the observable. I've named the parameter value and I'm just logging it to the browser console. If the observable encounters an error, it will pass an error object to the error function. I'm also just logging it, but with a label in front just so it's obvious that it's an error message. When the observable is done producing values, it will call the complete method. It doesn't accept any parameters, and right now I'm just having it log the message all done. It's important to note that an observable doesn't begin executing and producing values until an observer subscribes to it, so if I ran this code exactly as it is right now, nothing would happen. I've got an observable and an observer, but until I subscribe to the observable, they'll both just sit there. Since that doesn't make for much of a demo, I'll add a call to the observable's subscribe method and pass it the observer I created. To see this work in a browser, I need to start the Webpack dev server with the npm script I showed you earlier. In the VS Code terminal, I'll just type npm start. That takes a couple of seconds to bundle the code and get the web server started. Once it's done, I'll jump over to my browser and go to localhost:8080. I'll open the browser developer tool so we can see the output being sent to the console. You can see here that each value from my array was produced by the observable and passed to the next method on the observer, which logged it to the console. Once all of the values were produced, you can tell that the completion handler was called on the observer because we also got the all done message. This code works fine, but there's a shorthand version of this I think you'll see more often, so I want to go ahead and show it to you now. Rather than declaring a variable to store an observer, you can actually just pass the same three functions to the subscribe method, and RxJS will create an observer for you behind the scenes using those functions. I'm going to select and copy these functions. I'll then delete the observer inside the call to subscribe and paste in the three functions in its place. They don't need these names, so I'm going to delete them. RxJS assumes the first function you pass is next, followed by error and complete. With that in place, I can now delete my observer variable. I'll hop back over to my browser and show you that the results are the same. Because Webpack is automatically reloading everything, we're already seeing the new results, but just so you know I'm not doing any video trickery, I'll refresh the page and you can see I still get the same results. I now want to show you how you can create your own observable from scratch. I'll use the same array of numbers as my source data, but let's imagine I want my custom observable to only produce even numbers, and then it should report an error if it encounters an odd number. I'll comment out this line that creates the existing observable. I'll then declare a new observable variable named even numbers and assign it the value returned from a call to observable.create. That function takes a function as a parameter, which itself accepts a subscriber object as a parameter. I'll use another code snippet to paste in the body of the function. Remember that the subscriber object implements the same interface as observers. Calling next, error, and complete on the subscriber is what causes messages to be sent to the observer. The first thing I'm doing in this function is looping over all of the values in the nums array. Inside the loop, I'm using the remainder operator to see if the current value is evenly divisible by 2. If it is, I know it's an even number, and I produce it from the observable by passing it to the next method on the subscriber. If it's not evenly divisible by 2, I call the error method on the subscriber and pass it a message reporting the error. Once the loop has processed each value in the array, I call the complete method to let the observer know there are no more values. One important thing to note here is that an observable can call error or complete, but it will never call both. As soon as an error is reported, the observable stops executing and won't produce any new values or completion messages. The last thing I need to do before we can test this code is change the name of the observable I'm subscribing to down here to be even numbers. Okay, I'll go back to the browser and you can see that my custom observable is producing the same output we saw before since all of the numbers in the array are even. Just so we can see how it behaves with an error, I'll go back to the code and change the number 8 in the array to be 9. I'll jump back to the browser one more time and you can see that Webpack has already refreshed the page and now I have different results. The first 3 values in the array were produced just as they were before, but when the observable got to the number 9, it reported an error which was then logged by the observer. Notice that since I got an error, I did not get a completion message. Now that I've shown you the basic operation of observables and observers, let's see how to apply some operators to observable data. In this demo, I'll create an observable that produces click events and then apply several operators to the produced data. I'm going to continue writing code in the same file I used in the last demo, but I'm first going to comment out all but the import statement at the top. All of the code will be available in the course download materials. I'm going to add the from event function to the import statement and use it to create a new observable that will produce a click event every time someone clicks on the document in the browser. I'll now subscribe to this observable using the same technique I showed you in the last demo. I'll use another code snippet to paste in the functions that will handle the values, errors, and completion messages. I'm again just logging everything to the console for the sake of simplicity. At this point, I'm not applying any operators to the data being produced, so when I click on the document, the event object that's generated will be passed to this next function on my observer and logged without any modification. I want to show you what that looks like before I go any further. The app is already running, so I'll just jump back to my browser. I'm using a little video effect here just to help you visualize when and where I'm clicking inside the browser. As I start to click, you can see the event objects get logged down below in the console. They're logged as mouse events. I should mention that this is just a standard browser event object and doesn't have anything to do with RxJS. I'll expand one of them so you can see some of the properties on it. Let's imagine for a moment that I'm really only interested in where I clicked. There are a couple of properties here named Client X and Client Y that contain the X and Y coordinates of the point I clicked on. I want to focus on the X coordinate. It turns out there's an operator that will pluck a single value off of an object and just have the observable produce it, so I don't have to be bothered with everything else on the object I'm not concerned with. That operator happens to be named pluck. All of the operators in RxJS can be imported from the same location, rxjs/operators. Because I want my observer to receive the data as it exists after the operator has done its work, the call to subscribe needs to happen after the operator is applied. I'll move the call to subscribe down to the next line and add a call to the pipe method onto the observable. Inside pipe is where you list the operators you want to apply in the order you want to apply them. I'll add a call to pluck. It takes one parameter, which is the name of the property I want to pluck off of the event object. I want the client X property. What's now going to happen is that the original observable is still going to produce the same mouse event object, but before they're sent to my observer to be logged, they'll be passed to the operator that takes just the property I'm interested in and returns a new observable that only produces those properties. That's the observable I'm now subscribing to. Let's take a look at the new output. Now as I click around on the document, the only thing being logged is the X coordinate of the point I clicked on. That's much simpler to look at and work with if that's the only data I'm really interested in. Let's now add another operator and refine it a little more. Let's imagine that, for some reason, I happen to care about the amount of time between each value being produced by the observable. There's an operator that will tell you exactly that. It's named timeInterval. I'll add it to the list of operators I want to import. I can have it applied to the data after the pluck operator is applied by just adding a comma after pluck and calling timeInterval. It doesn't require any parameters. Let's see how that changes the output. Now when I click around, instead of getting just the X coordinate, I'm getting this timeInterval object that has two properties. The value property has the X coordinate, and the interval property contains the number of milliseconds since the last value was produced. That's potentially interesting if your app cares about such things. Let's pretend I'm not crazy about the structure of this object and would prefer it be reformatted as a string I could show to users. I'll go back to the code and import the map operator. I'll then chain it onto the timeInterval operator. The object passed to it will be the timeInterval objects we just saw. I'll use a template string to grab the value from that object and format it to show the number of seconds since the last value with the X coordinate after that in parentheses. Okay, let's now check the output one last time. As you can see, I'm now getting a nicely formatted string in the output telling me how many seconds since the last value, and it still shows me the X coordinate of the point I clicked on. I think you have to agree that this output is pretty different than the raw mouse event object I started with. Let me just say that I chose these operators just to give you a sense of the variety that exists and how quickly you can transform the data from a source observable into something potentially more useful for your app. These particular examples are admittedly a bit random, but I hope they helped you see the potential usefulness of operators. Okay, I know that was just a couple of quick demos, but I didn't want you to get through even a high-level course like this without getting a feel for the syntax used with RxJS. I also hope you've begun to see how the big pieces of the library fit together. Let's next talk about where to go from here to continue learning about RxJS. I hope this course has given you a good understanding of what RxJS is, what it's used for, and where it fits in relation to other libraries and frameworks. I also hope you've seen that the library is very approachable and something you could begin using right away on just about any client-side web application. If you think RxJS may be right for your project and you're ready to take the next step, I've got another Pluralsight course that goes into much more detail and includes lots of demos and code you can download. RxJS Getting Started focuses more on the specifics of using the library and covers additional topics I didn't present here, such as creating your own operators, multicasted observables, and testing your RxJS code. Another helpful resource you may want to bookmark is the official RxJS documentation located at rxjs.dev. Also, take some time to create some small test projects to play around with. Attempting to write your own code is one of the best teachers around. Okay, that wraps up this course. I hope you've enjoyed it, and I hope you'll give RxJS a try. Thanks for watching.
Buffer time, as you would expect, allows you to use a delay or an interval as the signal to emit the values that have been collected in the batch. As with most of the buffer operators, a new batch is started. Looking at first the plain buffer operator, this is going to collect the values emitted from our source observable and emit them whenever the inner observable emits a value, which is our signal. Here we can see that A and B are collected, and when our inner observable emits at 1, they're emitted as an array to whatever is subscribed. Same thing for C and D and E and F, with E and F being emitted because the source observable has completed. Taking a look at this in code, we have our source observable as an interval. It's going to emit values every roughly 100 milliseconds. We then use pipe to introduce our operators. Buffer, we pass in an interval observable that's going to emit every 1 second, roughly 1,000 milliseconds. That's going to be our signaling operator. That's going to say when do we shut down the current batch, emit it, and start a new batch. We're using take just for this demo to limit the life of our source observable, and then we simply subscribe. And the output is going to be 3 arrays of roughly 10 items each. And it's roughly because of the details of exactly when interval fires and things like that, JavaScript timers. So if we run this, just by using node, you can see our collection of arrays, 0 through 8, 9 through 17, and 18 through 27. So each of those is emitted when that inner interval fires, and it represents the values emitted from our source, which fire every roughly 100 milliseconds. Buffer count is going to be similar to buffer, except that in this case the values are stored until the batch is full, which we designate by the number parameter we pass into buffer count. When that number of items have been stored or the source observable completes, the values from the batch are emitted as an array. Buffer count allows us to specify the number of items in a buffer. You can see we have our require statements up top, pulling from RxJS or RxJS/operators. We have 2 examples here. The first is just a basic simple use of buffer count, where we specify a buffer size of 2, and then we just log the output. You can see we're going to get output of our first batch of 1 and 2. The second batch is just 3 because the end of our source observable comes through. So that source observable completes, and so the batch is emitted. Example 2, and we'll see these run in just a moment, but example 2 makes use of an optional parameter on buffer count. We specify that every time something is emitted, we're going to start a new batch. What this is telling us is that we can have multiple buffers. Multiple buffers can coexist. So we're doing the same source of 1, 2, and 3. We pipe that into buffer count, we specify a buffer size of 2, but then we use that, as I said, optional parameter to say every time we get a new emission from source, start a new batch. So when we log the output, we now get a batch of 1 and 2, another batch of 2 and 3, and then our final batch just of 3. Taking a look at these, running them through node, you can see the output is exactly what we saw in the comments. In the first example, we have just a buffer size of 2 specified, so we get 1 and 2, and then our final batch of 3. When we specify the optional parameter, we get an additional batch because we start a new one after the first item is emitted and after the second item is emitted. So a buffer size of 2, we get 1 and 2, and then we get 2 and 3, and then we get 3 when the source observable completes. Buffer time, as you would expect, allows you to use a delay or an interval as the signal to emit the values that have been collected in the batch. As with most of the buffer operators, a new batch is started when the previous is emitted, unless the batch was flushed because the source observable completed or erred. Buffer time allows us to work on buffers being time-based. So again, we have our interval as our source. It's going to emit every second. We pipe that. We take 6 just to limit the lifetime for this example. And then in buffer time, we say that we're going to emit every 2,000 milliseconds, and we're going to create a new buffer roughly every 1,000 milliseconds. So our output is going to be an array of 2 values except for the first and last. Taking a look at that run through node, we create our buffer every second and emit every 2 seconds. So the first and last are only going to have 1 value, and then the ones in the middle are each going to have 2 values inside our array. Buffer toggle is a little different from the others because you specify both the opening and closing of the batch. Values in the batch are emitted when it's closed, but unlike the other buffer operators, a new batch is not immediately started. You need to specify the point at which a new batch is started in the form of a signaling observable. When it emits, a batch is opened. Closing the batch is similar. When the closing observable emits, the batch is emitted and closed. In our marble diagram here, we open a batch, then close it at the 1, which causes A and B to be emitted. We then immediately open a new batch, which closes at 2, emits C and D, opens a new batch, and so on. This is going to be useful when we don't need to process every value emitted from the source, but just certain ones that we can define based on our criteria for opening and closing the batch. Maybe we only grab new items to process when we finished processing the previous batch, and anything in between is dropped. or maybe the contents of a batch define when we open and close the next batch. Whatever our requirements, this operator gives us a lot of control over the values we receive in our subscription. Buffer toggle is a little more complicated because we specify the opening and closing, but it's not bad. So here you can see that we define our open and closing signals. Opening is an observable that is going to emit every 400 milliseconds. We're using the tap operator, which we'll look at in a different module, just to be able to show when we're actually opening a new batch. Closing is going to be a factory function that returns an observable that signals when we're going to close that batch. So we're opening a batch every 400 milliseconds, and we close it 300 milliseconds later. And again, we're using tap just to signal or to be able to write out when we're closing that batch. Our source observable emits every roughly 100 milliseconds, again using tap to log to the console when it emits. We then call buffer toggle and pass in our opening and closing signalers. We use take just to limit the life of the source observable for this demo, and then we simply log the output. Now, taking a look at this when we run it through Node, there's a little bit more going on, but once we've gone through the code, you can see that what's happening is our source observable emits 0, 1, and 2, and then we open our first batch. It then emits 3, 4, and 5, and we close our batch. So when we close the batch, 3, 4, and 5 are in there, and they get emitted. There's then a gap before we open the next batch of roughly 100 milliseconds. So 6 gets emitted, but it's not included in any batch. We then open our next batch, 7, 8, and 9 are emitted from our source, and we close. 7, 8, and 9 now get emitted. So you can see this is showing how you don't have to include every single item coming out of your source in a batch. Depending on how you set your opening and closing signalers, you could exclude certain items. Buffer when is similar to buffer toggle, except that we only specify when the batch closes. A new batch is immediately opened after the current one closes, so we don't have the option of skipping values from the source. Every value will be in a batch. It's also similar to the vanilla buffer operator, except that we specify our closing notifier by passing a factory function as a parameter to the operator. That function is called when a new batch starts, and it's used to determine when the batch closes. This adds a dynamic nature to our batches because that factory function can provide a different closing signal observable for each batch to signal when it should be closed. Maybe that's providing a variable time in the fixed time of buffer time, or a variable batch size in place of the fixed batch size in buffer count. In our marble diagram here, we're emitting letters A through F from our source, and our signal observable emits at 1, 2, and 3. The result is that our subscription receives 3 arrays, A, B, C, D, and E, F. Buffer when lets us determine the closing point of a buffer, and that can Buffer when is similar to buffer toggle, except that we only specify when the batch closes. A new batch is immediately opened after the current one closes, so we don't have the option of skipping values from the source. Every value will be in a batch. It's also similar to the vanilla buffer operator, except that we specify our closing notifier by passing a factory function as a parameter to the operator. That function is called when a new batch starts, and it's used to determine when the batch closes. This adds a dynamic nature to our batches because that factory function can provide a different closing signal observable for each batch to signal when it should be closed. Maybe that's providing a variable time in the fixed time of buffer time, or a variable batch size in place of the fixed batch size in buffer count. In our marble diagram here, we're emitting letters A through F from our source, and our signal observable emits at 1, 2, and 3. The result is that our subscription receives 3 arrays, A, B, C, D, and E, F. Buffer when lets us determine the closing point of a buffer, and that can be a variable time period, or number of items, whatever we want to use as our signal to close the buffer. It can be determined programmatically and changed depending on the requirements that we have. So we set up a variable x, just going to be our counter of the number of items emitted from our source observable, which is an interval emitting roughly every 500 milliseconds. As we've seen before, we're using take just to limit the life of that source observable for our demo. We're using tap to set the value of x to the integer that's been emitted from interval. And then we use our buffer when. And here we pass in a factory function. And it looks at the value of x, the first 5 items coming out of the interval. We're going to use a batch size of 1 second. So we're going to emit the batch after a second. For anything after the first 5, we're going to use a batch size of a half a second, roughly 500 milliseconds. So we're going to see this as we go through that less than 5, we're going to have 2 items in the batch just based on the timing. And then after that, we're only going to have 1 because our batch size matches the interval of our source observable. So running that in Node, we have 2 items in our batch. And then once we get above the first 5 items, we end up with only 1 item in our batch. And again, that's because we're varying the size of our batch based on how many items have been emitted from our source observable. Looking at first the plain window operator, this is going to collect the values emitted from our source observable and emit them whenever the inner observable emits a value, which is our signal. Here we can see that A, B, and C are collected, and when our inner observable emits at 1, they're emitted as an observable sequence to whatever is subscribed. Same thing for D and E, except that these are emitted because the source observable has completed. Taking a look at this in code, we're going to use interval as our source observable for demonstrating the window operator. So you can see we have an interval emitting every 100 milliseconds. We use pipe to pass that through the window, and we use another interval emitting every second or every 1000 milliseconds as our signal to close the buffer. We use take just to limit the life of our source. We'll come back to the switch map in just a moment, but if we take a look at how this runs right now, you'll see that what we end up with is going to be our different observables. Because remember, window, unlike buffer, emits an observable. If we wanted to see the actual values inside that observable, we would need to do something to be able to get to the values, something like switch map. Now, when we run this with node, we're going to see the actual values that come out of our interval, our source observable. So the difference between window and buffer is that buffer emits things as an array, and window emits them as an observable. Window count is similar to window, except that in this case the values are stored until the batch is full, as designated by the numeric parameter we pass into window count. When that number of items have been stored or the source observable completes, the values from the batch are emitted as an observable. Taking a look at window count in our code here, you can see that we are setting up our source as a timer. We're going to take 9 items out of it. We pipe that into window count, and we specify a window count of 2. So our buffer is going to emit every time we get 2 items in it. It'll close, emit, and open a new buffer. We use switch map so we can see the actual values by piping that to an array, and then we just simply log to the console. Running that in node, we're going to get our buffer of 2 items, and then the last one only has 1 item because our source observable completes, and therefore the buffer is emitted. Example 2 down the bottom here, I'm going to let you run that on your own. What that's doing is specifying that we're going to be opening a new buffer every 3 items, and the buffer has 2 items in it. So the end result is that we skip one of the items. So our output is 0 and 1, then 2 is skipped. We start a new buffer, and 3 and 4 is emitted, and then 5 is skipped, and 6 and 7 is emitted. So you can take that, uncomment that source code, and run it if you want to look at that optional second parameter for how often you're going to create a new buffer. Window time, as you would expect, allows you to use a delay or an interval as the signal to emit the values that have been collected in the batch. As with most of the window operators, a new batch is started when the previous is emitted, unless the batch was flushed because the source observable completed or erred. Using window time, we can specify a time-based criteria for emitting our buffer. So you can see we set up our source as a timer that's going to emit every 100 milliseconds, and we're going to take 9 values out of that. We pipe source through window time, specifying our buffer size of 200 milliseconds. We then use switch map to convert that into an array so that we can see the actual values inside the buffer, as opposed to just seeing the observable object that window time emits. If we run that through node, we get our buffer emitted every 200 milliseconds, and because source is emitting every 100 milliseconds, we have 2 items in each emission from the buffer. Converted to an array, we see 0, 1, 2, 3, etc. The last item, 8, is emitted when the source observable closes, when we've taken all 9 items out of it, and it only has 1 item because it's never hit that second 200 milliseconds, or never hit the second emission that we got at 200 milliseconds. Window toggle is a little bit different because you specify both the opening and closing of the batch. Values in the batch are emitted when it's closed, but unlike the other window operators, a new batch isn't immediately started. You need to specify the point at which a new batch is started in the form of a signaling observable. When it emits, a batch is opened. Closing the batch is similar. When the closing observable emits, the batch is emitted and closed. In our marble diagram here, we open a batch, then close it at the 1, which causes A, B, and C to be emitted as an observable stream. We then immediately open a new batch, which closes at 2, and emits D and E as a stream. Like buffer toggle, the variable aspect of opening and closing batches provided by window toggle gives us a lot of control over what gets emitted from our source observable. Window toggle, we specify the opening and closing signals for our window. You can see our openings is a timer, emits every 500 milliseconds. Closing is a factory function that is going to emit and say, close that buffer 200 milliseconds after it opened. We have our source as a timer that emits every 100 milliseconds. Pipe that through take just to limit the amount of stuff coming out of our source for this demo. And then we pass that into window toggle, specifying our openings and our closings, and convert it to an array just so we can see the actual values and log out the values. So over here, if we run this with node, we can see items getting dropped between that 200 millisecond and 500 millisecond point. So we don't get 3 and 4, we don't get 7 and 8, 12, 13, 14. It's going to depend on the actual firing of the different timers and some of the variability of timers in JavaScript. But you can see that we're just grabbing certain values coming out of this. We're not getting every single value that gets emitted from our source every 100 milliseconds. Window when is similar to window toggle, except that we only specify when the batch closes. A new batch is immediately opened after the current one closes. Unlike window toggle, this means that every emission from the source will be in a batch. We just control the size of the batch by controlling when the batch closes. In our marble diagram here, we're emitting letters A through E from our source, and our signal observable emits at 1 and 2. The result is that our subscription receives two observable streams, ABC and DE. Just like buffer when, this operator is dynamic and gives us a lot of control. Taking a look at window when in code, we have our source observable as a timer that emits every 100 milliseconds, and we take 9 of the values out of that. We have our notifier as a factory function that is going to emit every 200 milliseconds. So then we pipe our source through window when, pass in notifier, and that's going to say every 200 milliseconds, close a buffer, emit it, and open a new buffer. We use tap just to be able to output when a new buffer is created, and then merge all to collect all the results and allow us to subscribe to them and write them out to the console. Taking a look at that, if we run it through Node, what we get to see is where that notifier fires, and we get a new buffer created. With our source emitting every 100 milliseconds and our notifier firing every 200 milliseconds, we get 2 items in each buffer being emitted until we get to the last one where it's emitted because the source has closed. There are 7 operators that can help you work with errors in your streams. We're going to take a look at each of them in this module. Welcome to error handling. Here are the operators that come into play when considering exception conditions or potential exception conditions in RxJS. Now, there's a couple of other operators that could be used in exceptions, but I chose to categorize them elsewhere because they have other broader purposes. Generally, the operators we're looking at fall into 2 broad use cases, either handling errors when they occur and responding in some fashion, or bypassing error conditions altogether. The most basic of these operators is the simple catch error. It allows your code to be notified when an error occurs in the source stream and react by either passing the error along or emitting another observable. In either event, it prevents an unexpected or unhandled stoppage in the stream. In our marble diagram here, we have A, B, and C being emitted by our source, and then an error gets thrown. We have our catch error operator set up to fall back to another stream, which begins emitting 1, 2, and 3. So any subscribers are going to receive ABC and then 1, 2, 3. They're not even going to know that an error occurred. We could also, if we chose, rethrow that error. Depends on what our needs are. In our example here, we have catch error set up in 2 different scenarios that we're going to take a look at. In the first, starting on line 9, we simply throw an error, and then we pipe that through catch error, through that operator. And in this case, we're going to log out that we caught the error, and then we're going to rethrow it. And you can see we then have a second catch error in our pipe, and that's going to grab that rethrown error, log it out, we've made some modifications to it, and then we just return of undefined. What that allows us to do is the series of values coming out of the source observable will not be interrupted. Despite the fact that we're throwing an error explicitly, this source observable never fails. We're never going to see the error handler, in which in this case is just going to log out the word oops. We're going to see that we caught the error, we rethrew the error, and then it's going to complete successfully. We'll take a look at that in just a second after we look at the second example, where we actually have an error that gets thrown, because as the values are emitted out of our source observable, A works fine, we can call 2 uppercase on that, but when we try to call 2 uppercase on the number 1, it throws an error. In this case, we just immediately return of undefined. So when our subscriber grabs those values coming out, it's going to get an uppercase A, it'll log that out, that's fine, and then it's going to get undefined, in which case it's not going to log anything out, and then that's the end of our source observable. So it just completes. Taking a look at that over here in Node, you can see we catch the error, we rethrow the error, and then we just complete. We never see that oops handler. Same thing for the second example. We see the first value coming out of our source observable, the uppercase A, that gets handled properly, and then we just complete, because the undefined doesn't get logged out, just because of the way we have the code set up. So catch error allows you to determine when an error has happened, do whatever is appropriate, which could be just ignore the error and move on. It allows you to let your source observable complete without the error handling ever being called. Throw if empty is pretty self-explanatory. If your source completes without emitting anything, this operator will force that to be considered an error. Normally that would be acceptable. Nothing says that your source must emit something before it completes. So this operator gives you that capability. We'll cover two different operators that let you handle timeouts later in this module, so this isn't for timeout situations. This is the source explicitly completing without emitting anything at all. Throw-if-empty is pretty straightforward. Here we're explicitly setting up an empty observable. We pipe it through throw-if-empty, and the results when we run it through node is we get our error message logged out that says no elements in sequence. We're explicitly saying if our source doesn't emit any values, we're going to consider that an error, and we're going to throw an error. Despite the well-warranted bad reputation of the phrase on error resume next, there are situations when dealing with streams where it's necessary to do just that. Unfortunately, that's not exactly what this operator does. A more appropriate name might be something like on error switch to, because that's a little closer to what it does. If an error occurs in your source observable, this allows you to jump over to a new observable or series of observables and emit those instead. But even that name isn't quite right, because here's the really wacky part about this one. It also switches over to the alternate observable when the source completes successfully. So a more appropriate name might be on close switch to. So be careful with this one. It doesn't do what you would reasonably expect it to. One more thing. You'll never see the error from the original source. If it's thrown, it's just going to be swallowed, and you'll switch over to the new observable. If it's not thrown, you're going to see A, B, and C, and then it's going to go to 1 and 2. If the error is thrown, you see A, B, and then it switches over because of the error, and you'll see 1 and 2. So this one's a little bit tricky. Just be aware of some of these details, and you'll be okay. Here's a look at our slightly problematic on error resume next. We set up our source as a stream of feed 1, feed 2, feed 3. We set up our backup stream. It's going to have a couple strings in it. And then we are going to subscribe to our source, pipe it through map, and do a quick comparison. When we get to feed 2, in this case, we're going to explicitly throw an error. Now, as the error message says, we're never going to see that error message. We then pipe it through the on error resume next and specify that backup stream to switch to when the error happens. So taking a look at this, when we run it in node, you can see we get feed 1, that's fine, and then we get to feed 2 and the error gets thrown. So now we're going to switch to our backup, which includes the handle error, but we don't complete the original. We don't get any information on the thrown error. And now this last part is going to come into play if we don't throw the error. So let's change our comparison here to say feed 2A. Save that and rerun. Now the error doesn't get thrown this time. We see the complete feed 1, feed 2, feed 3, but then we also see the backup. So this is where I was saying that on error resume next is a bit of a misnomer because it's going to complete and it's going to switch over to the backup even if we get through successfully our source. Retry is pretty straightforward and useful for things like HTTP requests that may fail due to network issues. Retry lets you say, if my source throws an error, just go ahead and resubscribe to try again, up to a certain number of retries. Here we see retrying twice, but the source continues to error after A and B have been emitted, so eventually we see the error. And that's an important thing to know. If the source continues to error out, you'll eventually see the error when all of your retries have been used up. Taking a look at retry, you can see we set up a source observable with the values A and the number 1. We pipe that through map and attempt to call to uppercase. Well, obviously that's going to fail when we try to do it on the number 1. But then we pipe it through the retry and say we want to retry twice. So when we go ahead and run this, we're going to see our first capital A, that's for the original attempt, and then we see 2 more letter A's, and those are the retries, because it's going to start over again at the beginning of that source observable. And then finally, after the 2 retries, we see the error message written out. So retry is going to give us the ability to say, let's go back and resubscribe to that source observable, but it's important to remember that it starts at the beginning of that observable. Similar to retry, except that this operator allows you to decide whether you should close the source observable, either with an error or successfully, or continue to retry. It does this by taking a factory function as a parameter. That factory function will receive whatever error is thrown by the source observable, and then that function can do one of 3 things with the observable it returns. It can error out, in which case the source observable will error out as well, and the subscriber will receive the error. It can complete, in which case the source observable will complete successfully as well. Or it can just return, in which case the source observable will be retried. In our example marble diagram here, we have our source emitting A and B, and then erroring out. In the middle, the retry when on the first pass signals that the source should be retried. But then on the second pass, it's going to give up and error out, which causes the source observable to error out, so we see the error in our subscriber. Taking a look at retry when in code, there's a lot going on in this example, so I'm actually going to run the example over in the console first, and then we'll walk through the code and be able to see the results as we go through the code. So if I go ahead and run this, we're going to get it attempting to process the results coming out of our interval. And now let's go through the code. There's generally going to be 2 sections here. We're going to start with the first where swallow error is set to true. So in the beginning part, we take our source observable that's going to be coming out of the interval every 200 milliseconds. We pipe that through map. we write out what number we're attempting to process. And the first time through, x is going to be 0, so we just return it, and we can see attempting 0, successfully processed 0. We're then going to get the next emission out of the source observable, and it's going to be 1. So we attempt 1, and now we're going to throw our error. And that's when retry when comes into play. So here we're going to have swallow error set to true, so we're going to take a look at this block here. We return the value coming out of the errors.pipe. Here we use the tap operator just to log out the error message that we got. And then we're going to check our retry count, which is incremented by scan, and we look at scan and tap both elsewhere in the course. But essentially, scan is just going to keep track of how many times we've been through here. So we check our retry count. If it's equal to 2, we're going to swallow the error and just complete the observable. The first time through, retry count is going to be 1, so we say we're going to retry the whole source, and we specify this is retry number 1. The second time through, scan increments our counter to 2. We say if retry count equals 2, then we're going to swallow the error, and we're going to exit out. We then return retry count. Either way, coming out of tap, we're going to return that value. Take while we look at elsewhere in the course, but essentially it's going to take values that are passed through it until that expression is no longer true. So the first time through, our count is less than 2, so it's going to continue. It's going to essentially go back and retry, allow us to retry. The second time through, our count is not going to be less than 2, so that's false. It's going to complete that inner observable, which causes the source observable then to be completed, and we exit out. We complete successfully. So if we scroll down, we're going to see our subscribe down the bottom here. We're going to log out that we completed successfully if that source observable completes successfully, which in this case, that's what happens, because our retry when completes that inner observable. Now, if I go and change this to not swallow the error, save it, and run this again, now we're going to get our error logged out. You can see down at the bottom we're failing, and we get our error message. We come in here, and in this case, the if swallow error is now false, so we go into this else. Same thing, errors.pipe, we're going to log out with tap. We're going to use scan to keep count of how many times we've been through here. Then we're going to use tap again to take a look at our retry count. The first time through, retry count is not equal to 2, so into the else, and we just say we're retrying. The second time through, retry count is equal to 2, so we're going to log out that we're failing, and we're going to throw an error coming out of our inner observable, in which case the source observable is going to be made to throw that same error, and we're now going to, in our subscriber, we're going to get the error callback to process. So that's where we get the 3 asterisks and the error and the message written out. So that's a look at retry count. It's a little bit convoluted in here. I would suggest that you go through this example a couple of times and get a feeling for take while is completing our observable when error count is no longer less than 2, and that causes the source observable to complete. Otherwise, it's going to leave the observable open, which is going to cause retry when to retry the source observable. The timeout operator works in one of 2 ways, depending on what you pass as a parameter. If you pass a number, timeout will use that as the number of milliseconds you want your code to wait between values being emitted from the source observable. As long as values keep showing up within that time frame, the timeout operator will just pass them along. If there's a lull that exceeds the number of milliseconds you specify, a timeout error will occur. Our marble diagram here shows this option. A and B will be emitted, but then there's a delay until C is emitted, and our timeout period elapses before that occurs. So the error gets emitted to our subscriber, and C is never received. The other option is to pass a date value as the parameter. In this case, the timeout operator doesn't monitor the time between emitted values. Instead, it looks for the source operator to complete before the provided date value. If it does, it's as if the timeout operator wasn't even there. If the source doesn't complete by the provided date value, then the timeout error will occur. I have 3 examples for taking a look at timeout. So we'll start with the first one here. And this one, everything actually succeeds. So we don't actually see the timeout occur, but I wanted to show you what this would look like. And the setup for all 3 of them is going to be very similar. We start with our source observable that's going to emit A, and then it's going to get 3 different set timeouts to emit B, C, and then finally complete. And that's going to be at 100 milliseconds, 200 milliseconds after that, and then 300 milliseconds after that. When we come down and actually pipe our source observable through the timeout operator, you can see we're saying if it doesn't emit values every 350 milliseconds, then set timeout is going to throw an error. But because each of those is happening in less than 350 milliseconds, we're never going to see an error. So when I run this, we go A, B, C, and complete. Everything worked as we would expect it to. Coming in and taking a look at timeout 2, the only difference here is that I changed the timeout to 150 milliseconds. So we're going to get A, we're going to get B, because they both happen in less than 150 milliseconds, but then there's a 200 millisecond pause before C gets emitted. And so we're going to get that timeout error before C. So taking a look at this, we get A, B, and then the timeout occurs. The last one we'll take a look at is using the other option for specifying a parameter. In this case, we specify a date. So set up the same, we're going to give it a source observable, it's going to emit A, B, C, and then complete at 100, 300, and 600 milliseconds. But when we set up our timeout, we set up a new date, which is basically now plus 500 milliseconds. So if it doesn't complete within 500 milliseconds from when it runs, then it's going to throw an error. And as you can probably guess, we're going to see a problem for that 600 millisecond wait time. So if I go ahead and run this one, we get A, B, and C because they all happen within the 500 millisecond time frame, but then the timeout happens before we complete. So that's a look at the different ways that you can have a timeout set on your source observable. Timeout with is just what you would expect. It's the timeout operator, but instead of throwing an error, it switches over to a backup observable. This can be useful if you want to, say, retrieve values from the server, but if they take too long, just use a set of predefined defaults until the server's responding again. In our marble diagram, we see A and B emitted successfully, but then a delay before C is emitted. If our timeout period expires in the middle of that, we're going to fall back on 1, 2, and 3 and never see the value C or an error. Our subscribers will never know that the timeout occurred. They just keep receiving values. Taking a look at timeout with, a similar setup to what we had with the timeout operator, where we have our source observable that's going to emit A, and then there's 3 different set timeouts that are going to emit B, C, and then complete at 100, 300, and 600 milliseconds. We set up our timeout with operator on line 18 to say if you don't get an emission every 150 milliseconds, switch over to our fallback, which is going to be set up on line 8 as the lowercase ABC. So what we're going to get is we're going to get a capital A, a capital B, because they both happen within 150 milliseconds, but then there's actually a 200 millisecond pause before C gets emitted. So timeout with is going to kick in and switch us over to the fallback, and we're going to get the lowercase letters from that point forward. Go ahead and run this, and you can see that's exactly what we get, but we complete successfully. As far as our subscribers are concerned, an error doesn't happen here. There's no real timeout. We're essentially saying we're just going to switch right over and start giving you the values out of this fallback. Often when working with streams, you don't need or want to process every value. And that's where the operators in this module come in. They let you filter the stream to a subset of items based on the criteria you specify. There are 15 different operators in this module, but 1 through 4 and 5 through 8 are each 2 sides of the same coin, so pretty straightforward. For the rest, the 3 distinct operators are pretty similar, and then we have filter, sample, audit, and throttle. And the last 3 are confusingly similar. We're going to take a look at each of these, so let's get started. Starting with the very basic skip operator. Skip does exactly what you would expect. You provide the number of values that you don't care about, and that number will be filtered out from the beginning of the source observable. In our marble diagram here, we specify 3 as our parameter to skip, and so A, B, and C are dropped and never seen by our subscribers. Taking a look at skip, we start with an observable that's going to emit 3 values, 1, 2, and 3. We pipe it through skip and tell it we want to ignore the first 2 values, so those are going to get dropped. We're just going to log out the output. So if I go ahead and run this over in the console, you can see that the only value we get emitted is the 3. We've dropped the 1 and the 2. Skip last is the opposite of skip. The number we specify is how many values get dropped from the end of the stream. Here we specify 3, so D, E, and F get dropped. Now this is one of those operators that isn't going to work for infinite observables. The observable has to end in order to have it drop the last 3. We have 2 examples for skip last. The first is just basic usage. We start with an observable that's going to emit the values 1, 2, and 3. We pipe that through skip last and say we want to skip the final 2 elements. We then just subscribe and log out the results. And as you would guess, the output that we're going to get is just the number 1, 2, and 3 are skipped. We'll see this run in just a second, but first I want to take a look at the second example that shows what happens if you have an observable that never completes. What does skip last do? So we have an interval set up going to emit every 100 milliseconds. We pipe that through skip last, tell it we want to skip the last 1 item, and then we just log the output. And as you would probably expect, this is going to run forever. We're going to see all of the values emitted from interval written out to the console because the observable never completes. So skip last does nothing. If I go ahead and run both of these, we'll see the first example. We've skipped the 2 and the 3. And then here we have our never ending unless I force node to shut down. But we have our never-ending observable. Interval is going to keep emitting. It's never going to complete, so skip last does nothing. There's nothing for it to skip because there's no last element. Skip until is a dynamic skip. Instead of specifying a number of values we want to ignore, we provide a second observable as a parameter to skip until. Every value emitted from our source observable will be ignored until that second observable emits. From that point on, every value is accepted and passed on to our subscribers. In our marble diagram, observable as a parameter to skip until. Every value emitted from our source observable will be ignored until that second observable emits. From that point on, every value is accepted and passed on to our subscribers. In our marble diagram here, A, B, and C are ignored because that inner observable hasn't emitted yet. Once it emits, everything after that from the source gets passed along, so D, E, and F are received by our subscribers. Skip while allows you to evaluate the values coming in from your source and use them to determine whether you should skip. One thing that's important though, this is a one-time determination. Once the supplied predicate function evaluates to false, every value after that is accepted and emitted to the subscribers. An ongoing evaluation of values for filtering requires the filter operator, which we'll look at a little bit later in this module. Once the value of 5 is evaluated, the predicate function is false, so everything after that is emitted, even if they would make the predicate true again if it were to be reevaluated. With skip while, it's not reevaluated once it's gone false. Taking a look at skip while, we have an observable created with of, going to emit the values 1, 2, 3, 1, 2, 3, 4. We pipe that through skip while and specify a condition that we're looking for our value to be less than 3. We then subscribe and write all the values out to the console. As I indicated in the comment on line 11, our condition becomes false at that first 3. So skip while toggles at that point, and we stop skipping values. So we get the 3 and then the 1, 2, 3, 4 as our output. If I go ahead and run this, you can see that's exactly what we get. The 1 and the 2 are skipped because those keep the condition for our skip while true. As soon as it flips to false, the values start being emitted. Take is the opposite of skip. Here we provide a number value as a parameter, and that's the number of items that will be accepted from the source and passed along to our subscribers. With take 3, A, B, and C are passed along, and then the source observable is completed at the conclusion of the take operator. So the rest of the values aren't actually emitted. We've seen take in some of our other examples for other operators because I've used it to limit the number of values that were emitted from a source just for the sake of controlling things for the demo. But here's an example of looking at take all by itself. So we set up our source as a timer that's going to emit every 100 milliseconds. We then pipe that through take and say we're going to take 5 values. We subscribe, we log out any of the results that we get to the console. We also log out when the source completes. So you can see that when we get to the number of values specified by take, the source observable is then closed and completed. So running this over in Node, we get our 5 values and then we get the complete. That's going to make sure that things get unsubscribed once we've received the number of values that we want out of our source. Take last jumps us to the end of our source and provides the final n values to our subscribers. Obviously, this is only going to work for finite observables. If you use something like interval as your observable source, There's no concept of a last item. It just continues emitting forever. So you can't take the last n. This won't throw an error. It will just never end or emit. We have 3 examples for take last. Starting with our first, we set up a source as an observable of values 1 through 9. We then take that and pipe it through take last and say we want the last 3. We subscribe, simply log the values we receive out to the console, and then log when things are complete. The output that we get is just the last 3 values, 7, 8, 9, and then complete. Scrolling down a little bit to take a look at example 2, we have an observable of 3 values, but then we pipe that through take last and specify 5. Now take last isn't going to throw an error here, it's just going to give us the only 3 values we have. So even if take last specifies a number larger than the source observable emits, we're still going to get those values. We'll get whatever came out of the source observable. And then our last example, we set up a source as an interval emitting every 100 milliseconds, and that's never going to end. So we can see when we pipe it through take last and say we want the last 5, well, we're never going to get anything because interval doesn't have a last value. So if I go ahead and run this, you can see this is exactly what we get. We get 7, 8, 9, and then it's complete. We get 1, 2, and 3. Now here I didn't log out the complete. It does actually complete. I just didn't happen to log it out. And then in our last example, it will sit there forever because interval is emitting every 100 milliseconds, and take last is waiting for it to end, and it never does. Take until adds a dynamic nature to our process. It allows us to provide a second observable as a parameter, and the operator will keep passing along every value until that provided observable emits. In our marble diagram here, the values from the source observable at the top are emitted and passed along to subscribers until the second observable emits at the blue circle with the exclamation point. At that point, the source observable completes and is unsubscribed. No more values will be passed along. For take until, we set up a timer as our source. It's going to emit every 100 milliseconds. We pipe that through take until and specify an internal observable, a timer that's going to emit at 300 milliseconds. So the result of this, after we subscribe, is that we're going to log out to the console all values emitted from our source until that internal timer emits at 300 milliseconds, and then we're going to complete. So we're going to get the values of 0, 1, and 2 from the timer emitted, and then the timer for take until is going to fire, and that's going to stop, and our observable is going to be completed. So running this in Node, we can see we get 0, 1, and 2, and then our source is completed. So that timer setup on line 8 is closed. Take while allows you to evaluate the source values coming in from your source and use them to determine whether you should stop passing the values through. As with skip while, this is a one-time determination. Once the supplied predicate function evaluates to false, the source observable is unsubscribed and no additional values are emitted to the subscribers. An ongoing evaluation of values for filtering requires the filter operator, and we're going to take a look at that a little bit later in this module. In our marble diagram here, the first 2 items are accepted because the predicate is true for them. Once the value of 5 is evaluated, the predicate function is false, so the source is unsubscribed, and everything after that is ignored, even if they would make the predicate true again if they were to be reevaluated. For take while, we have a source observable created with of. It's going to emit the values of 1, 2, 3, 1. We pipe that through take while and specify a condition that we're looking for the value coming out of our source to be less than 3. As long as that condition holds true, the values will be passed along to our subscribers. The subscriber here is just going to log it out to the console, but as soon as that condition goes false, the source observable is unsubscribed, so no additional values are ever emitted. So I'll go ahead and run this in Node, and you can see we get our 1 and our 2. Distinct allows you to eliminate duplicates from your stream. There are a couple of approaches to this. If you don't provide any parameters to distinct, then it will exclude all duplicates. If you provide a function as a parameter, it will use that function to determine what duplicate means. The function will receive each value emitted from the source observable in sequence, and then returns a potentially modified value, which is what is used for the comparison to determine uniqueness. In our marble diagram, we have a basic use. The second B and the second A are dropped and not emitted to our subscribers. We get a bit more advanced in our demos, so let's go take a look. We have 3 examples for taking a look at distinct, so I'm going to go ahead and run the code, and then we'll take a look at each of the examples and the output that they generate. Starting on line 7, we have our source observable set up with of, and it's going to emit the values 1, 2, 3, 3, 2, 1. We pipe that through distinct, and then simply log out the output. As you can see both in the comments and when I run it in code, we get only the values that are unique within the source. So it doesn't matter where they're emitted in the source, we're only going to emit unique values. So we get 1, 2, 3. We could also provide a function to determine how the values are compared. So in example 2, we specify our source observable of 1, minus 1, 2, 3, 2. We pipe that through distinct, and we specify a function. Here we're going to take each value and use the absolute value of that as our comparator. So then we just subscribe to that and log out the output. So getting the absolute value means that 1 and minus 1 are going to be the same, so we're only going to get 1 emitted. The 2 and the later 2, one of them is going to be dropped. And then the 3 is just emitted because there's no other conflicting values. So here also you can see in our output, we get just 1, 2, and 3. But that's an example of using a function to do our comparisons. In the third example, we set up objects to come out of our source observable. So a simple object that has a name and an isAuthor value. And we have 3 different objects, Dave, Mary, and Dave again. We pipe that through distinct, and here we specify a function that says we want to use the name property of each item as the value to be compared. So it's going to take a look at the name property of each object, and if they're unique, they'll get emitted. If it's been repeated, then the second one's going to be dropped. So you can see our output, we get the first Dave and Mary, and then the second Dave object is dropped because the name's been used already. Distinct until changed is a little different from the plain distinct in that it will only compare a new value emitted from the source observable to the immediately previous value. If they're different, the new value will be passed along. If they're identical, the new value will be dropped. In this case, it doesn't matter if the value had been emitted prior to the immediately previous value. The lookback window is only 1. In our marble diagram here, the second B is dropped because it matches the B emitted right before it, but the second A is not dropped because the value before it is a C. It doesn't matter that an A value was emitted earlier. So we have 2 examples for this. In the first example, we have our source set up emitting 1, 1, 1, 2, 1, 2, 3. We pipe that through distinct until changed and simply log out the output. Now we're going to get output of the first 1, and then the next 2 1s are skipped because the value hasn't changed. The 2 gets emitted because it's different from the 1, and then the 1 after that gets emitted, the 2 after that gets emitted, and the 3 after that gets emitted because each of those is different from the previous value. Scrolling down, taking a look at our second example, here we're using a mapper function to determine the value that gets compared to the previous value. So like with distinct, we're using absolute values here. So the first 1 gets emitted out of our source that's set up on line 20. The second 1, the negative 1, gets dropped because the math absolute value makes that the same as the previous value. The 2 gets emitted, the minus 2 gets dropped. And then the 1 and the 2 both get emitted because they're different from the immediately preceding value. So if I go ahead and run these in Node, you'll see we get the output that we expect from the comments. So in each case, each new value is compared only to the immediately preceding value that was emitted. If they're the same, the second value is ignored. If they're different, the second value is emitted. Distinct until key changed is similar to distinct until changed, except that it works on objects, looking specifically at the values of the property you specify for its comparison. If that value is different from one object to the next, the new object will be emitted. And we've got 2 different scenarios we can take a look at. Each is going to make use of this array of posts that we set up starting on line 8. And in each case, it's going to be post ID 3 on line 11 that gets dropped, for 2 different reasons. We'll take a look at those in the examples. In the first example, we set up our source as a collection of those posts that are going to get emitted. We pipe that through distinct until key changed and specify that we want to work off of the likes property. And then we simply log out the ID and the number of likes for each one that makes it through distinct until key changed. Now in this case, post ID 3 gets dropped because the likes is the same as post ID 2. So the second one is going to get dropped and just the first one is going to get passed through. So we get our output showing 1, 2, 4, and 5 as our post IDs. And as I said, 3 gets dropped. I'll go ahead and run this over a node so we can see that is in fact the output that we get. Now for the second example, we again make use of that posts array, set it up as our source. We pipe it through distinct until key changed, and we specify this time the author property. That's the one that we want to check to see whether or not our value has changed. We also specify a function to do the comparisons. So here we're going to get the value and the previous value supplied as parameters. And in this case, we do our comparison just a simple a.id equals a2.id. We subscribe and simply log out the post ID and the author ID. And again, if I scroll back up, take a look at our source, you can see it's reaching into that nested ID property inside the author using that comparison function that we specified. And again, post ID 3 gets dropped because the author ID is the same. It's 12 in both cases. If you look at the output over in the console, you can see we get the same posts, 1, 2, 4, and 5. And then we get the author ID, and each of those is unique. The filter operator allows you to get as fancy as you would like with your elimination of values from the source observable. You have to provide a predicate function to do the comparison. If it returns true, the value is passed along to the subscribers. If it returns false, the value is dropped. In our marble diagram here, our predicate function is simply testing whether each value is greater than 3. If so, the value is passed to the subscribers. If not, the value is dropped. Taking a look at the filter operator, we set up our source as an observable of the numbers 1 through 8. We pipe that through filter, and here we can specify any comparison function that we want. It's going to receive each value in turn coming out of our source and pass it through that filter function that we specify. If that function returns true, then that value is going to be passed along to our subscribers. If it returns false, then the value is going to be dropped. So here our function is just checking for evens. We subscribe and simply log out the output. What we get is just the even numbers. All the odd numbers are dropped. They're not passed along to our subscribers. Sample allows you to essentially ping the source observable at a given point and receive the latest value emitted. You specify the point at which you want to pull a value by specifying an observable as the parameter to this operator. When that observable emits, the latest value from the source is grabbed and passed along to the subscribers. Often this is going to be time-based. You want to pull a value every n seconds, for example. While you could do that with sample, there's actually an operator specifically for that scenario that we're going to look at later, sample time. Just plain sample can use any observable as a notifier. So maybe something like every time a value is received from the server. And sample has a fair amount going on, so we'll step through each piece to make sure that you understand what happens. We start with our source. As an interval, it's going to emit values every 100 milliseconds. And then we set up an observable as our notifier. And that notifier is going to emit values at 150 milliseconds, at 350 milliseconds, and then it's going to complete at 750 milliseconds. Now, if I scroll down a little bit, you can see we have our source. We pipe that through sample, and we specify the notifier that we set up above. Now we're just going to take 3 values just to control things for the demo, and then all we do is log out the output. Now let me go ahead and run this so we can see what happens. I'll scroll back up so we can see our source interval emitting every 100 milliseconds. When the notifier emits at 150 milliseconds, the last value emitted from our source was the 0, so that gets passed along to our subscribers. The notifier emits again at 350 milliseconds, and at that point the last value emitted from source was 2, so that gets passed along to our subscribers. And then finally, the notifier completes at 750 milliseconds, and so the last value there was the 6. So those are the values that get passed along to our subscribers. The other values get dropped because we hadn't pinged the source with our notifier to say, give me the latest value. Audit is like sample with one important difference. Like sample, audit allows you to ping the source observable at a given point and receive the latest value emitted. Unlike sample, audit takes a factory function as a parameter. That factory function will receive a value emitted from the source observable and must return an observable. The returned observable is used as the signal for when the next value will be accepted from the source. This is a little confusing, so let's take a look at our marble diagram, and then we'll go take a look at it in code. Assume that our source observable is emitting values every 1 second. On the first value emission, the value from the source observable, in this case 0, is not passed to the subscribers, but is passed to the function parameter of the audit operator. That function performs a calculation and returns an observable that will emit a value in, say, 2 seconds. Values coming out of the source observable are ignored until that calculated observable emits. When that calculated observable emits, the audit operator takes the last value emitted from the source, in this case 2, it sends that 2 value to the subscribers, but then uses the next value from the source, in this case 3, to calculate a new observable. For the sake of our example, let's say that the new calculated observable will emit in 3 seconds this time. Again, values coming from the source are ignored until that calculated observable emits. The process repeats again, emitting the previous value to the subscribers, and using the next value to calculate a new timeout observable. However, this time the final value 6 is emitted and passed to the subscribers, because after that the source observable completes. So in a sense, you can think of audit as a dynamic sample. This will make a little more sense when you see it in code, so let's go take a look. There's a fair amount going on with audit, so I'm going to go ahead and run this first over in our console so that we can take a look at the values that are being emitted as we walk through the source code. So we start by setting up our source as an interval that emits every 100 milliseconds. We then pipe that through first take just to limit the number of values output for the demo, but then we use tap to log out each value that gets emitted from the source. Finally, we get to audit, and audit is going to take in each value that was emitted and use that in a calculation. Ultimately, it needs to return another observable. In the case of what I have here, we're simply logging out, here's the value that would have been used, and we always return an observable as a timer of 500 milliseconds, and that's just for the sake of the demo. And then finally, when we subscribe, we can see the values that are actually emitted up to the subscribers. So we have three different things coming out: what comes out of the source, what gets used to calculate our next observable, and then what gets ultimately received by our subscribers. And you can see we get the initial value coming out of our source of 0. That gets emitted, but it never gets received by our subscribers. That 0 is used to calculate the next observable, and then the source continues emitting 1, 2, 3, 4, and then that timer that we had returned on line 12, our calculated observable, emits. So the subscribers are going to get the last value that was emitted, the 4, and then the 5 gets emitted from the source, and that 5 is used to calculate a new observable. Now this would continue on, but as I said, we limit it with the take on line 8 just to control things for the demo. So we see the values coming out of the source, we see what actually gets used to calculate our observable, and remember, audit has to return an observable. And then we can see the values that are actually received by our subscribers. Throttle is extremely similar to audit. The difference now is that the first value emitted is sent to the subscribers, and the next observable is calculated with the same value sent to the subscribers, which is always the previous value or the last value emitted from the source. Rather than try to walk through this again in the marble diagram, let's go take a look at the code example. Throttle is going to be very similar to audit, so what I'm going to do is actually rerun audit. So we have those results on the screen, and then I'm going to run throttle so we can compare them. The code that we have set up is nearly identical. The only significant difference is obviously that on line 10 there we're using throttle for this example instead of audit. Emitted is sent to the subscribers. Throttle is extremely similar to audit. The difference now is that the first value emitted is sent to the subscribers, and the next observable is calculated with the same value sent to the subscribers, which is always the previous value or the last value emitted from the source. Rather than try to walk through this again in the marble diagram, let's go take a look at the code example. Throttle is going to be very similar to audit, so what I'm going to do is actually rerun audit. So we have those results on the screen, and then I'm going to run throttle so we can compare them. The code that we have set up is nearly identical. The only significant difference is obviously that on line 10 there we're using throttle for this example instead of audit. So we can take a look at the results that get emitted. With throttle, we have 0 emitted from the source, same as audit. We have 0 used to calculate the next observable, same as audit. But in between there, we see that the 0 is actually passed along to our subscribers. So that's different from audit. That first value is passed along. We then have 1 through 5 emitted from the source in throttle. 5 is passed along to our subscribers and used to calculate the next observable. And then it's going to continue emitting values until, in this case, we end because of our take, or until the timer that we return on line 12 emits. So slight differences in the way that audit and throttle are used. The primary difference being that the initial value in throttle is passed along to the subscribers. Like in the last module, in this module, we're going to look at operators that let you filter values coming out of a source observable. Now, however, the operators are limiting the source to just a single value. Here are the 8 operators that serve primarily as a means of limiting a source to that one value. Most of them are pretty straightforward, but we're going to take a quick look at each one. Like I said, straightforward. The first operator does exactly what you would expect. It emits just the first value from a source and then unsubscribes. At its most basic, first is extremely simple. As we can see in example 1 here, we have a sequence that emits 5 values, but first is going to give us just the first value, so we get an output of 0. Taking a look at the second example, we're specifying a function as a parameter to the first operator now. So what we're going to get is the first value from our source that causes that function to evaluate to true. So the first even number is 10. 1, 3, 5, 7, and 9 are ignored, and 10 gets emitted as our first value. Taking a look at example 3, in this case, we're using the same function, but there are no even values in our source. So what we get instead is an error that there are no elements in the sequence. And that would happen if you called first on an empty observable as well. There's no first value. Taking a look at this running over in Node, you can see the output exactly what we saw in the comments. First time we get 0 and then complete. Second time we get 10 and then complete. And then the last time we get no elements in sequence. And another easy one, just emit the last. Unlike first, though, this won't work for an observable that never ends because there is no last from an infinite observable. Taking a look at last, we have a couple different examples for some different scenarios. In its most basic case, last gives us the last item that comes out of a given source. Pretty straightforward, we're going to get 3 here. We'll run these in just a moment. We'll take a look at the code first. In this case, we're going to take a look at providing a predicate function to our last operator. So we are looking specifically for even values here. And in this case, the last even value we get is the only one in the list. It's 2. Example 3. If we call last on an empty sequence, it's going to cause an error, similar to what we saw with first. One more example, if we call last on an infinite sequence, well, then we're going to get nothing because the sequence never ends. There's no last value. So it's just going to sit there forever. If I come over and run these, you get the values that we would expect, but notice that that last one is just sitting there. It's never returning me back to my prompt. It's because we're still waiting for a last value. It hasn't come in yet. Min allows only the smallest emitted value to pass along to the subscribers. Like last, this won't work for an infinite observable. Note that you can provide a function as a parameter to do the comparison to determine the minimum value. Min, pretty straightforward, gives us the minimum value out of a sequence. You can see in the first example that we have some negative values in there, so we're going to get a negative value as our minimum, -3. But if we wanted to pass in a function, we could use that same sequence and change the output by saying we want to take a look at the absolute value of the value that was emitted from our source. So in this case, we're going to get an output of 1 from min, because 1 is going to be the smallest value when you get absolute value tossed into the mix. Go ahead and run this with Node, and you see the output exactly what we would expect. Max allows only the largest emitted value to pass along to the subscribers. Like min, this won't work for infinite observables. Also, like min, you can provide a function as a parameter to do the comparison to determine the maximum value. So in the first case, the largest value in there is 8. We can also provide a comparator function for max, like we saw for min, but here we have an example of going in and working with objects. We're going in and checking the salary property and using that to compare to determine the employee with the largest salary. If we go ahead and run this, we get the output exactly what we'd expect. So the comparator function can get as involved as we want. It can go in and work with properties on objects, call other functions, whatever it is we need it to do in order to determine the max. This operator lets you emit only the value from the source observable from the specified position. Just be aware that the index is 0-based, so in our marble diagram here, element at 2 provides the third element, the 5. Also, unfortunately, you can't use this operator to get elements from the end of a stream by specifying a negative index. Element at gives us the ability to essentially go in and cherry pick a particular value. So we specify a number, but because the index is 0-based, we're going to get that number plus 1. So if we specify 2, we get the third value. As we see here, we get 3. Running this in Node, we get the third value coming out of our sequence. Like array.find, the find operator will allow just the first instance of a value that causes the predicate function to be true to be passed along to the subscribers. Once that first value is passed along, the source observable is unsubscribed, so no additional values are emitted. Find, we specify our predicate function, which can be as simple or complex as we need it to be. And when we send that into the find operator as a parameter, it's going to find the first item emitted from our source that satisfies that predicate, that causes it to evaluate to true. So here we're looking for a number greater than 2 that is evenly divisible by 2. In our source, the first value that meets that criteria is 4. So when we run this, we get our first matching value of 4. Similar to find, but instead of passing along the value, find index passes along the zero-based index of the first item that caused the predicate function to evaluate to true. So here we have our sequence. We're passing in a predicate function to find index, looking for items greater than 2 that are evenly divisible by 2. The first item that matches that criteria is 4, which is at an index of 3 because the index is zero-based. We go ahead and run this, and that's the output that we get. 3 is the first index of the item that matches our predicate function. The single operator is a little bit different than what you would expect. It emits one of 3 things: either the first value to cause the predicate function you provide to evaluate to true, undefined, or an error. It errors if there's more than one value that causes the predicate function to return true, which means that this is another operator that won't work on infinite observables. It emits undefined if the source emits values but none cause the predicate to be true. In our marble diagram here, the top example will have the value of 6 emitted to the subscribers because it's the one and only value in the stream that satisfies the predicate. The second example will emit undefined because no values match the predicate. And the third example will error because there are multiple values that cause the predicate to evaluate to true. Single can emit one of 3 different things. In the first case, if it finds one value that matches the predicate, it emits that one value. So we see that in our first example here. Of 1, 2, and 3 is our source, and we're piping that through single. We specify a predicate looking for even numbers. It has one and only one even number, so we get that value output, 2. If I go ahead and run this, you can see we get our output and then it completes. Taking a look at the second example, when no value matches, we have our source of 1, 2, and 3. Pipe that through single. We're looking for values that are less than 0. Well, none of them are less than 0, so we get undefined emitted. We can see that in the comment as well as in the code that I ran over in the console. And then the last situation that we can have with single is if more than one value matches, it's going to throw an error. So here we have of 1, 2, 3, 4, and we're again looking for even numbers, but we have 2 different even numbers that satisfy that predicate, 2 and 4. So in this case, we're going to get an error that says sequence contains more than one element. So those are the 3 things that you could possibly get out of the operator single. Grouping observables comes into play when you have multiple source observables and want to bring them together and emit their values as a single stream. There are multiple ways you can combine the values, and the operators in this module cover each of those scenarios. Like the other categories we've covered or will cover, there are certainly other operators which could conceivably be placed in this module, but for one reason or another, I chose to cover them elsewhere. Combine all takes an observable of observables as its source and emits the latest value from each observable when any one of the inner observables emits, provided each observable has emitted at least once. Now that sounds a little confusing, so let's look at our marble diagram before we jump over to code. In our marble diagram, when A emits, nothing happens because the other observable hasn't emitted yet. When C emits, the subscribers receive the latest value emitted from each source, so A and C. When B emits, the latest value from each is B and C. Then when D emits, the latest value is B and D. Taking a look at combine all in code, we're going to start with an example that actually doesn't return any values because our source 5 doesn't have any values in it. So when we try to combine all, even though source 6 is going to emit 1, 2, 3, the combine all is going to wait until both sources have emitted, and source 5 completes without ever emitting, so what we get is nothing. There's no output from this first example. We'll see that in just a second, but I want to scroll down and take a look at the second example, which does actually emit some values. So you can see beginning on line 23, we have 4 different sources set up. They're going to emit different values at different times. We've got intervals and delays and various other things going on in there. On line 28, we combine those into a single source, an observable of observables, and we pipe that through combine all, and then we simply output the value we get. You can see the output that we're going to get. Now, your output might be slightly different. It depends on the details of JavaScript timers and such, but it should be something similar to this. So if we go ahead and run this, we see the first example, nothing got emitted because that first source never had any values in it. And then below the line, we get our second example where we're going to get values emitted from the different sources. You'll notice that source 1, by the time everything emits, source 1 has gotten to 3. So that's the latest value from source 1. Same thing for source 4. It very quickly emits while the others are paused or delaying. Sources 2 and 3 are going to change, and here's where some of the differences might come in if you run this, depending on how your machine processes and the timing of the JavaScript timers. But we're going to get the latest value out of source 2. The first 3 times we run it is 1, and then we get a value of 2 for the last run. For source 3, we start with the value of 4, and then we get 5 and 6 twice. So that's taking a look at combine all, giving us the ability to take values from each of our sources and emit them as an array. Concat all will also emit all values from each source observable, but it does so serially, finishing one observable before beginning the next. In our marble diagram, A emits from the first observable, and then even though the second observable is next emitting C and D, those are held until the first emits B and then completes. Then C and D get sent along to the subscribers. Concat all is going to maintain the order of the values from each input and emit them in the order that the inputs begin emitting. Taking a look at concat all, you can see we have 2 different arrays, working days and weekends. And then we're going to concatenate them together. So we build our observable of observables on line 12, pipe that through concat all, and then even though the weekends observable emits essentially simultaneously with working days fires first, so it's going to finish that observable before it moves on to the values from the next. So we get Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So that's what concat all gives us, the ability to combine multiple sources into a single output. Exhaust takes an observable of observables as input and processes them in parallel. However, if one observable begins emitting before a prior observable is completed, that second observable will be dropped entirely. Think of it as the first observable to begin emitting gets exclusive access to the output stream until it's finished. And any other observable that tries to emit while the output is locked just disappears. All of its values are dropped. In our marble diagram, A is emitted and gets access to the output stream. C tries to emit, but it gets blocked, so the entire observable is thrown out. D is never emitted. Then B emits, and the first observable completes. So now the third observable can emit E and F. To demonstrate exhaust, we again have an observable of observables, source 1 and source 2. Source 1 is just ABC. That's going to be delayed by 100 milliseconds, though. And then source 2 is just D. We create our observable of observables on line 10. We pipe that through exhaust, and then we just log the output. Now, because exhaust is going to finish source 1, and if source 2 comes through while source 1 is still processing, then source 2 is just going to be dropped. Because of that, we just get ABC. We never see D. So if I run that through Node, you can see that's exactly what we get. D is just dropped entirely because it came through, it emitted, while source 1 was still processing. Merge all is like concat all that we saw earlier, or really it's the other way around. Concat all is like merge all. The difference is that merge all lets you specify how many input observables will be subscribed to concurrently, and concat all forces the concurrency to be 1. The values from each subscribed observable will be passed to the subscribers as they're emitted. If you were to specify a concurrency of 3, the results would look something like our marble diagram here. Each of the 3 provided input observables are subscribed to simultaneously, and their values are emitted in order, regardless of which source observable they came from. For merge all, if you don't specify a value for concurrency, then all inputs are subscribed to simultaneously. In reading about RxJS and streams, this process is often called flattening, taking multiple observables and combining them or flattening them down to one single output consisting of all values. So here we have 3 sources. One is a timer. We're going to take 10 values out of it. It emits every 1 millisecond. Next, we have an array of working days. We're going to take the values out of that, delayed by 15 seconds, and then weekends, delayed by 5 seconds. So we pipe all those through merge all, and we specify a concurrency of 3. Now, we would also get the same effect if we didn't specify a concurrency. If I come over here and run this, you can see we're going to get each of the observables, and their values are interspersed. Now, due to some of the timing, the details of JavaScript timers, your output is going to look probably slightly different from this, but essentially what we get is the values from the observables as they're emitted. If we were to try to make this look like concat all, we could come back and specify a concurrency of 1. Run this again, and you can see we're going to get the values. It finishes the first observable, then it goes on to the second, then it goes on to the third. With latest from has a source observable and 1 or more internal observables passed in as parameters. Every time the source observable emits a value, that value is combined with the latest value from each of the internal observables and emitted as an array. This is provided that each internal observable has emitted at least once. If one of the internal observables has not emitted, then nothing is emitted from with latest from. In our marble diagram here, when A emits from the source, the first internal observable has emitted a 1, but the second has not emitted anything, so nothing gets sent to the subscribers. When our source emits B and C, all of the internal observables have emitted, so the latest value gets sent to the subscribers. And you can see down the bottom, what the subscribers receive is an array of the values from each observable. There's a lot going on in this example for with latest from, so bear with me for a second here as we walk through the code. We start on line 8, setting up our source as a timer. It starts at 0 milliseconds, and every 300 milliseconds it's going to emit. We take 3 of those emissions, and we essentially just slap an A on the beginning of that, so it's going to be A and then whatever number came out of our timer. We then set up our first internal observable, also a timer, emits every 100 milliseconds. We're going to take 10 values out of that, and for that one we just slap a B on the beginning. Our second internal timer is going to just have the value of C, and we're going to delay that by 10 milliseconds. There are some console logs here that walk through what emits when. I'm not going to go through each of those in detail, but you can see at what points in time things emit different values, and then we can compare that to our output. You can see the output laid out in comments, but if I go ahead and run this, you can see that that's the output that we get. So a lot going on in this one. I would say take the code and kind of kick around, try different timings, see what different outputs you get. But in general, you're going to get an array of values from your source and each of your specified internal observables.